Hello, Geography 231 students. Welcome to week 13. So you may notice, if you have already explored the module for this week, that we are not doing raster data this week, as the syllabus says. I basically bumped week one of the raster analysis to next week, and I'm going to condense it down to just one single week. Reason being that we needed more time to cover all of the various regression analysis topics that I wanted to get to. So this is the first time I've taught this class, and certainly the first time I taught it online, and so I wasn't quite sure how much time it was going to take to get through regression. I probably should have given myself more time, so I ended up doing that. I called an audible and decided to bump 1 week of raster, but have no fear. We will get to raster data next week, and for those of you that have taken 232 already, it's really going to be more or less review, and for those that have not taken 232, it's really going to be kind of an introduction to techniques and methods that you're going to be using a lot more next semester. So I don't feel too bad cutting off 1 week of raster analysis, because you're going to have so much of it next semester. And so I'll still be able to cover the basics. We're still going to do an entire lab next week. But for this week, I basically have kind of continued the topic from last week, certainly continued the same lab format. So I didn't do a tutorial this week. It's going to be the same format from last week. It's a lab that I've adapted from an Esri lab. But we are going to cover two different regression techniques this week that we didn't talk about last week. That's going to be exploratory regression and geographically weighted regression. So just to mention there, just to kind of highlight there. So next week we'll get into raster analysis. This is week 13, and it's going to be more regression. So if you look at your syllabus and it doesn't add up, that's why week 13 has been changed. Okay. All right. So this week we are doing regression analysis part 2. Okay. Exploratory regression and GWR, just geographically weighted regression. This week's lecture is going to be a continuation, as I said, of what we talked about last week. No tutorial this week because it's going to be the same techniques that you employed last week. This week's lab is called Use Exploratory Regression and GWR, and as I said, I adapted it from Esri, so it's going to be very thorough, and I think it's actually very, very informative, very useful, so I think you get a lot out of it. Upon completion of this lecture and lab, you should understand what is exploratory regression analysis, what is geographically weighted regression, and understand more regression analysis techniques. So a quick regression analysis recap from last week. So as I mentioned last week, most GIS analyses deal with where questions. Where are features on the landscape? Where are phenomena occurring? Okay, so analysis techniques such as proximity, overlay, even hotspot analysis, those determine locations of features and phenomena, whereas regression is asking why. These are why questions. Okay, so instead of saying where's the best site for a new store, or where are crime hotspots, or where is a specific disease more prominent than others, we're asking why. So why is this the best location for a new store? Why is that a crime hotspot there and not somewhere else? Okay, and why is this disease more prominent than others in a given location? Okay, so regression allows us to ask why. It doesn't always answer exactly, but it gives us probabilities. And that's the thing I really want to kind of drive home this week that I didn't probably highlight enough last week, is that regression, the outputs of regression, the data that you get when you run those reports, they essentially are giving you probabilities. It's probability theory, saying that with 95% confidence or 99% confidence, this is the explanatory variable that's affecting the dependent variable. And you might think 95%, 99% probability, that's real high, right? You can feel good about that. And you can, but you have to think about this in terms of replicability, right? So can a study be replicated? Can it be rerun and end up getting the same results every time? That's really how science is oriented, right? So if you run a research project and you've got some hypothesis and you've got all your various independent variables, now if you find that X variable has a 99% probability of affecting the dependent variable, but then you pass on your methods to somebody else and they try it in a completely different scenario with a different, in a different location, maybe different circumstances, that 99% is real high unless it gets done over and over and over and over. So imagine running your same regression model 100 times. If it's 99%, there's going to be one time when that null value is rejected, and it shouldn't be, right? Think about it 1,000 times, right? In that case, you end up with even more. Okay, so just be aware that 99 or 95% certainty, it's all about probability. It's not actual fact saying these are the explanatory variables. It's that these are likely the explanatory variables, and that's really the thing I just want to make sure is clear. Okay, and I'll touch on this later on in the lecture as well. So regression analysis can help us understand which factors contribute to a phenomenon and determine the extent to which each factor contributes to that phenomenon within a probability. So last week we discussed a commonly used statistical analysis tool known as ordinary least squares, or OLS regression. OLS regression uses probability to analyze how much of the dependent variable explains the combination of explanatory variables provided. To find a properly specified model, which is another way of saying a valid model, right? Properly specified means it checks all those 6 checks, right? You must perform the 6 statistical checks on the OLS results. A properly specified model is a model that you can trust because it passes all of the checks, right? It's essentially you're doing a checklist of saying, okay, so this is correct, this passes this, that, and the other, okay? Another analysis method, exploratory regression, finds the best combination of explanatory variables and determines whether any models for the explanatory variables provided passes all 6 checks. So the 6 statistical checks you perform after running OLS provide a framework for verifying the results of exploratory regression. Okay, so exploratory regression, I'm going to talk about this a bit more, but essentially it allows you to test the water. So if you've got 5 independent variables, it runs combinations of those, and it tries to find the best combination to explain, or as explanatory, to explain the phenomenon that you're trying to explain. So exploratory regression. To find a properly specified regression model or a set of explanatory variables that you know that you can trust, you must run OLS, perform the 6 checks, and understand which statistics to examine. However, running OLS on a set of variables and performing the 6 checks can be repetitive and time-consuming. Another option for locating a properly specified regression model is known as exploratory regression. Exploratory regression runs OLS on all possible combinations of explanatory variables and shows which variables pass the 6 checks. Okay, so it runs them on combinations. That's the key thing to know. So if you got 5 different variables, it's going to run variable 1 and 2 together, 1 and 3 together, 1 and 4 together, 1 and 5 together, 2 and 3, 2 and 4, 2 and 5, and so on and so forth. Okay, so it finds the right combination to best pass the 6 checks. All right, so remember that AIC number from last week. The goal is to find the lowest AIC and the best adjusted R-squared number for your combinations. So the associated diagnostics, as I said, AIC and adjusted R-squared, can also help you choose the best passing model. So exploratory regression checks each of the following specified explanatory independent variables. It looks at adjusted R-squared, coefficient p-values, the VIF, the variance inflation factor values, the Jarque-Berra p-values, and spatial autocorrelation p-values. Okay, so each of those p-values basically has to do with certainty. So exploratory regression runs OLS on every possible combination of explanatory variables for models. Each model is assessed against specified criteria parameters that you choose. When the exploratory regression tool finds a model that exceeds your specified adjusted R-squared threshold, a model with appropriate coefficient p-values for all explanatory variables, model with appropriate coefficient VIF values for all explanatory variables, and model with appropriate Jarque-Berra p-values, it then runs the spatial autocorrelation tool on that model's residuals. Okay. If the spatial autocorrelation p-values meet your search criteria, the model is listed as a passing model. Okay, so it still runs the 6 checks. It still looks at the adjusted R-squared, the Jarque-Berra to look for any sort of skewing on if it's equally distributed. It looks at the VIF and it looks at the coefficients. Okay, and it creates a coefficient for every one of the independent explanatory variables as well. So a couple of things to be aware of when using exploratory regression. Be aware that exploratory regression is somewhat controversial from a scientific method viewpoint. And here's why. So there are basically two schools of thought on this. There's the scientific method viewpoint and what we call in the GIS field the data miners, or really it's kind of the data science field. This would be the data miners viewpoint. Okay, so these are two different ways of looking at regression analysis, and it kind of depends on really what academic field you're in. Are you in data science, or are you in hard science that has a very established hypothesis? Okay, so strict scientists might object to exploratory regression because it relies too heavily on inductive reasoning. If you think back to week 1 of the class, I talked about the difference between inductive and deductive. And inductive reasoning essentially collects data and starts to look for patterns, and then it pulls out hypotheses from patterns that have already been collected or observed on the landscape. Conversely, deductive has a really hard and fast hypothesis, and then basically it says, do the phenomena that I'm observing, do these confirm or disconfirm my hypothesis? Okay, so if you're a strict scientific method person, you may have problems with exploratory regression because essentially it's feeling for patterns. It's looking for patterns that you haven't already decided on. You haven't already said, okay, this is what I want to find. It's saying I'm open to patterns that I have yet to establish or yet to observe. Okay. So this perspective says you should formalize your hypotheses before exploring your data to avoid creating models that fit only your data but do not reflect broader processes. So again, the key thing is to make sure that a model is replicable, right? That it is reproducible in other circumstances. Experiments must be replicable and reproducible under varying circumstances in order to be considered valid. Okay, so if you have a model that works great under very specific conditions, then there may be a problem with your hypothesis. Essentially, it's very tailored to some certain situation, and it doesn't have broad applicability, meaning that it may potentially be invalid. Furthermore, regression statistics are based on probability theory, and this is what I just got into a little while back. And when you run thousands of models, you strongly increase your chances of inappropriately rejecting the null hypothesis. This is known as a type 1 statistical error. Okay, so I already mentioned this, but basically when you have a 95% confidence level, you're accepting a particular risk, right? And if you run your data 100 times, 5 out of 10, you may accidentally reject the null hypothesis when you shouldn't. You end up saying that, okay, well, this is not caused by random variables or random situation, but actually it is, right? So if you could resample your data 100 times, probability indicates that as many as 5 out of 100 samples would reproduce false positives. When you're running even more models, like 1,000 for example, you end up with potentially 50 that are false positives. Okay, so just be aware of that 95% or 99% confidence level. It may not be as conservative as you think when the experiment gets reproduced over and over and over. Okay, so as you increase the number of models, you diminish your ability to draw conclusions from your results. So that's the caution from the hard scientific method perspective. On the other hand, researchers from the data miner school of thought may believe it's impossible to know all the factors that contribute to any given real-world outcome. So often the questions we're trying to answer are complex, and the theory on a particular topic may not even exist yet. So if you are going at this from an inductive reasoning standpoint, you may not have a hard and fast theory yet, right? There may not be a hypothesis yet. You just know that there is some interesting phenomena that's correlating with others, and you're going to investigate it through regression and see what comes out, right? So data miners, which are usually data scientists or users and producers of what we call big data, are proponents of inductive analyses, such as those provided by exploratory regression. Exploratory regression methods allow for hypothesis development in real time. Okay, so instead of going in with it already established, you start to create your hypothesis based off of what you are observing in the data. All right, so recommendations. So exploratory regression, when used with caution and discretion and humility even, is a valuable data mining tool that can help you find a properly specified OLS model. Okay, so simply because I brought up these cautions, it doesn't mean you shouldn't use exploratory regression, but just be aware of its potential downfalls, right? Calibrate your regression models using a portion of your data and validate it with the remainder, or validate your model on additional data sets. The exploratory regression tool in ArcGIS Pro has the advantage of looking for models that pass all of the OLS diagnostics described rather than only assessing one or two, okay, like just the R-squared, adjusted R-squared values, okay? So you can be fairly confident that the probabilities that you're getting are accurate, but you can't read more into them than what they actually are, which is just a chance, right? A high probability is still probability. Okay. Global versus local regression models. So global models, like OLS regression, like we talked about last week, only take non-spatial data into account. Okay, so OLS does not factor in location. It's not about where features are on the landscape. It's only about the dependent and independent variables associated with the data set. But there may be times when you need to actually take physical location of features on the landscape into account. Okay, so OLS regression is what we call a global model because it describes the overall data in a study area, the data relationships in a study area. So when those relationships are consistent across the study area, the OLS regression equation model models those relationships well. Okay, so if it's uniform across the whole study area. When those relationships behave differently in different parts of the study area, the regression equation will not model the whole area accurately. You have to take local regional differences into account. So when explanatory variables exhibit regional variation, meaning they vary from place to place within a study area, global models decline in accuracy because essentially you're looking for one equation to fit an entire study area, even though perhaps we'll say population is clustered in one corner, or the wildfires are only occurring in one part of the county and not in another part of the county, right? So when the relationship between the explanatory and the dependent variables varies regionally, the relationship is known as non-stationary. Okay, so non-stationary data essentially means the relationship is dynamic and changes over space, so over the spatial, the area, over space. Okay, when dealing with non-stationary data, it's important to use a local analysis method to account for regional variations. So OLS is usually the way to start, generally speaking, regardless of whether your data is regionally varied, it's non-stationary. Still start with OLS, but you may find that the AIC number for your dependent variable will actually improve if you try a local analysis method instead. And what local analysis method am I talking about? GWR. Okay, so geographically weighted regression. It fills the need to account for regional variation. So GWR, geographically weighted regression, is a local regression model that assigns one regression equation to each feature in a study area. And when we talk about features, it's going to be polygons generally, right? So if you've got, we'll say, a map of California, that you could run a GWR regression equation for every county, for every zip code, for every census tract, whatever, right? You're not just applying one single regression equation to the entire state, because as you know, Southern California differs from Central California, and Central differs from Northern California, and Inland California differs from Coastal California. That's just the way that the Earth works, right? So depending on where you're at, you're going to have different local conditions than somewhere else. So in contrast, OLS is a global regression model that uses one regression equation for all features in the study area. OLS is an appropriate place to start your regression analysis, but its inability to take non-stationary data into account means it may not always be the most appropriate tool on which to end your analysis. So my advice would generally be to start with OLS always, and then once you find out how accurate that regression equation is for your study area, then you can decide, do I want to go the GWR route? Maybe I should do some exploratory regression to find out which variables are the most impactful, but generally start with OLS. So GWR regression. Geographically weighted regression works by allowing model coefficients to vary regionally. As I've said, essentially GWR runs a regression for each location rather than a single regression for the entire study area. So essentially you can view it as this. So if this is the study area, instead of having one single regression equation for the whole area, you actually would have multiple equations for every single county or city, whatever we're looking at. So when should you use GWR? The equation for GWR indicates that the predicted values and the coefficients are for a single geographic location. Since every location in a study area has its own coefficients, you can map these values quantitatively, okay, and you will in today's lab. So essentially you can do like choropleth or graduated colors based off of the various coefficients that are assigned to each polygon. So for example, if you were predicting in which counties low birth weights are likely to occur, and you know that your independent variables vary across your study area, you would want to use GWR in that case. So GWR might be appropriate when the Concord test statistic has an asterisk. So the Concord test is one of the tests that runs in OLS. All right, so you look for the statistic to indicate, you look for the asterisk rather to indicate statistical significance. So always look for the asterisk anytime you run regression analysis, right? So the Concord test statistic has an asterisk next to it after running OLS. The test statistic has statistically significant non-stationality, meaning that that Concord test is saying that the data varies significantly from place to place. In that case, you probably should try GWR. Okay, so look for that. GWR might be appropriate when you're predicting future values from current values. Okay, and finally, GWR might be appropriate when you have found a properly specified model using the same explanatory variables. So in that case, you might need to run, that says fun, you might need to run exploratory regression to find the best explanatory variables. So interpreting GWR results, what do the results actually mean? All right, so the good thing is that GWR always produces a feature class. Basically polygons, right? Within the feature class attribute table, fields are added for each explanatory variable that stores the coefficients. GWR feature classes can be symbolized based off the coefficients for each exploratory variable, which you will do in today's lab. And the symbology is a visual representation of where the relationships are strongest and weakest. Okay, so how does that actually look on the landscape? What we have here is a map of eastern South Dakota. Okay, so this is the GWR results for premature death in eastern South Dakota. Okay, so the dependent variable, the variable about which we are trying to explore causes, is premature death. All right, so in this first map we see vehicle accidents and premature death have the strongest regression relationship in the southeast. Okay, so one might assume that perhaps speed limits are higher there. Maybe the roads are of a lower quality. It could be many things. Here we see suicides and premature death. Well, that could be any number of things. I would assume it would have to do with where populations are, so this could also be a population map of South Dakota. Or there could be some other causal factor there. Maybe rates of depression are higher because of, alcoholism or who knows what. This is liver disease and premature death. This one I found the most fascinating because there's essentially a linear distribution of counties north to south. So what is that all about? I don't know enough about South Dakota, but you could speculate. Maybe it has something to do with the natural landscape. Who knows? Or people just like to drink along that freeway there. I don't know. And lastly, we have heart disease and premature death. So in this case here, it's very much skewed toward the southwest. So it's kind of intriguing. So at least this gives you a kind of an example of when you use GWR, which you will in the lab, it helps you find where the strongest relationships are between the dependent and the independent on a local level. Okay, so it's not for the entire state. It's for individual polygons. Oh, and there's the last one: poverty levels and premature death. In this case here, this may correlate with tribal lands where incomes tend to be lower. I don't know for sure, but it's a pretty fascinating distribution. So I'll just go through one more time just to kind of give you just a quick look. So we've got vehicle accidents, premature death skews toward the southeast. Suicide skews toward the southeast and the northwest. Liver disease, linear skew right through the middle. Strange. Heart disease to the southwest. And lastly, we have poverty levels skewed towards the northwest. All right. So here's your regression tool comparison. It compares OLS to GWR. I'll not go over that. That's more just for your own reference. But that concludes part 2 of regression analysis. There is obviously a lab this week. There is no tutorial, but it's the same same style as last week. You will have to, once you get through part 2, you're going to need to export maps using 4 different coefficients, and you're going to symbolize on those 4 coefficients. Export the maps preferably to JPEG, because then you can pop them into a Word document, and in that same Word document you can answer these 3 questions here. It's all in the assignment, which is posted in the module, so not to worry. But at any rate, have a good one. We are on, geez, what do we have? 3 weeks left? My goodness, crazy. Next week is our last week of lecture and lab. Week 15 is what I'm considering just open lab period. I know we're not actually in the lab, but basically there's no assignment for week 15, and that's to give you that last week before finals, give you the full week to work on your project. So make sure you take advantage of that. Let me know if anybody wants to do any more Zoom meetings or has any questions via email. Always here. And that's it. So have a good one. Bye-bye.